You see, there's a question that has been lingering in my mind, and perhaps in yours too. If space-time is the invisible stage on which the entire universe performs, then what does it feel like to stand upon that stage, moment by moment, without ever noticing its presence? It's strange, isn't it? We spend our days walking through rooms, crossing streets, aging gently from hour to hour, and yet the very fabric carrying us forward remains hidden. Well, that's the thing. We live inside a structure so grand, so subtle, that we mistake it for nothing at all. And still, behind every memory you hold, behind every breath, behind the quiet ticking of your body's internal clock, space-time is shifting, stretching, curving, reacting, like an ocean whose waves we rarely learn to see. And you know, when we look up at the night sky, those distant sparks, some long gone, some newly born, we're not just seeing space. We're looking backward through time itself, peering along the ripples and folds of a cosmic landscape that began long before any of us were here. Perhaps that's why it feels almost sacred, this act of wondering. Because once you notice space-time, really notice it, you begin to sense that you are part of something vast, something dynamic, something that is continuously sculpting the paths of stars in the quiet rhythm of your own heartbeat. So maybe the real question is this: what happens when we finally pay attention to this hidden architecture of reality? When we allow ourselves to drift into the idea that space is not empty, that time is not simply passing, but that both are woven together into a living, breathing structure that carries the entire story of the universe. And in 2025, standing here, wherever here happens to be for you, we can take a moment to explore that story together. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple: to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. You see, when we talk about space-time, people often imagine something distant, abstract, maybe even a bit cold. But, here's the quiet truth I keep circling back to. Space-time is not out there. It is the very thing holding you in this moment. And I suppose the best way to begin is simply to ask you to notice the room around you. Notice the distance between you and the nearest wall, the weight of your body where you sit or lie, the slow, drifting sense of time you feel inside your thoughts. These sensations seem ordinary, almost trivial, but they are your first contact with the fabric of reality itself. Well, you see, we humans grew up believing that space was just empty volume and time was a neutral stream moving steadily forward. We imagine ourselves walking through space the same way we walk across a floor, and we imagine time as a calm river carrying us along at one unchanging speed. But that picture, familiar as it is, belongs more to our biology than to the universe. Our eyes evolved to detect light, not curvature. Our minds evolved to sense danger, not the geometry of the cosmos. And so the real structure around us remains mostly hidden, like a deep ocean beneath a thin raft of intuition. Perhaps the simplest place to begin is with the idea that space and time are not separate at all. They are fused, intertwined, inseparable, like threads woven into a single cosmic cloth. You cannot move through one without moving through the other. Even now, as you breathe, your motion through time is as natural as the drifting of planets through space. In fact, the universe does not track where you are or when you are. It only keeps track of your path through space-time, the four-dimensional trail you carve simply by existing. And that's the thing. Once you start seeing space-time as a unified whole, the world becomes less like a static stage and more like a living landscape. Imagine a vast terrain, stretching in every direction, but not made of soil or stone. Imagine instead a landscape made of possibilities, where each point is a crossroads of where and when. Time is not a clock. It's a direction you are compelled to travel. Space is not emptiness. It's the shape of the path laid before you. Together they form a continuum, and you are always moving through it. You know, People often ask why space-time exists even when there is no matter inside it. Shouldn't space collapse if there is nothing to hold it apart? Shouldn't time stop if nothing changes? But space-time is more fundamental than matter. It is the stage on which matter appears, the container in which events unfold. Even in a region devoid of stars, planets, or dust, space-time is still present, still stretching, still capable of bending. In that sense, the universe does not need content to exist. It needs structure. And space-time is that structure. Now imagine placing something massive in this fabric, something like a star. Most of us were taught to think of gravity as an invisible force pulling things together. But in the deeper truth revealed by relativity, gravity is not a force at all. It is the curvature of space-time caused by mass. If you place a heavy ball on a stretched sheet, the sheet bends, and anything moving nearby naturally rolls inward. In the cosmos, the concept is similar, but the geometry is four-dimensional and far more profound. The star does not pull you. The star shapes the space-time you travel through, and you simply follow its curves. When light travels through the cosmos, it too must obey this geometry. Light does not choose its path. It takes the straightest possible route allowed by space-time. But when space-time bends, the meaning of straight changes. Light curves around galaxies, arcs along gravitational wells, dances through the warping of the universe itself. This is not because light is weak, but because space-time is sovereign. You could say the cosmos writes the script, and everything else, photons, planets, people, play their parts. And here is a remarkable thought. Space-time can stretch, compress, twist, and ripple, reacting dynamically to every ounce of matter and energy. It is not a rigid container. It is supple, responsive, alive in its own quiet way. In the early universe, space-time expanded faster than light itself, carrying matter outward like dust caught in a cosmic tide. Today, it still expands, and the galaxies drift apart, not because they are moving through space, but because the space-time between them is growing. Perhaps the most subtle idea of all is that space-time is not empty. Even when devoid of particles, it contains structure, energy, and potential. What feels like nothing is actually a quantum field simmering with activity. Virtual particles flicker into existence and vanish before they can be caught. Energy flows in delicate fluctuations. Space-time hums with possibility. The vacuum is not blank. It is pregnant with physics. And if space-time can vibrate, then it can ring. The universe can shake, ever so gently, when massive objects collide. These shakes are gravitational waves, ripples traveling across the cosmic fabric at the speed of light. They stretch and compress space as they pass through us, though so faintly that only the most sensitive instruments ever notice. For billions of years, these waves have crossed the universe, carrying with them the faint echoes of ancient cataclysms, allowing us to listen to events we can never see. Hold that image for a moment, because it tells us that space-time is not merely the background of reality, it is one of the main characters. It has behavior, it has texture, it can be excited, disturbed, sculpted. It plays an active role in the unfolding story of the universe. And once you sense that, even faintly, the universe feels less mechanical and more like something deeply interconnected, where everything touches everything else through the medium of space-time. But, let me offer you a more intimate example. Right now, your body experiences the downward pull of Earth's gravity. But in the language of space-time, you are not being pulled at all. You are being held in place while space-time falls around you. The planet curves the fabric beneath your feet, and the straightest path through that curved geometry leads downward. If the ground were not in the way, you would simply follow that path. Falling is not being dragged. Falling is following the natural shape of space-time. And your sense of time, your heartbeat, your thoughts, your aging, is also wrapped into this geometry. Time does not tick the same way in every corner of the universe. Near massive objects, time slows. High above the surface of Earth, time runs faster. Even the satellites that guide our navigation must adjust their clocks because they orbit where space-time is a little less curved. The passage of time is not absolute. It is a negotiation between you and the shape of the cosmos. Perhaps the most humbling idea in all this is that no object, no particle, no sliver of reality exists outside spacetime. Everything we know, everything we can imagine, every story ever told, every memory ever formed, all of it is woven into the same fabric. You are a thread in the tapestry, your life a short but luminous streak across the four-dimensional stage. And when we finally allow ourselves to see space-time in this way, as something dynamic and alive, the universe becomes less like a distant spectacle and more like a strange and beautiful companion walking beside us. We begin to sense that there are hidden depths everywhere, even in the quiet moments of our daily lives. The simple act of existing becomes a kind of cosmic dance. Now, as we drift from this understanding toward the next layer of the story, a new question begins to rise, gentle but insistent. If space-time behaves this way, if it bends, curves, shapes the flow of time and light, then what deeper principles govern this behavior? What ideas, discovered by a certain quiet thinker in the early 20th century, revealed the true nature of gravity as geometry rather than force? Well, you see, that leads us naturally into the next chapter, where we begin to explore how one revolutionary insight reshaped our understanding of the universe forever, and how relativity revealed the hidden rules by which spacetime plays its cosmic game. You see, as we move from that gentle recognition that spacetime is alive with structure and motion, we arrive at a turning point in our journey. Because someone, more than a century ago, looked at the universe with a kind of quiet stubbornness and asked a question so simple it almost seemed childish. What if gravity is not a force at all? And that question, well, it cracked open reality. It lifted the curtain on a deeper truth and revealed a universe more fluid, more elegant, and far more surprising than anything classical physics had imagined. And this someone, as you already know, was Einstein. You know, the extraordinary thing about his insight is that it didn't rely on complicated machinery or exotic experiments. It was born from thought, from imagination, from wondering what it would feel like to chase a beam of light or to fall freely in an elevator. And, slowly, through these strange daydreams, he realized that gravity was simply the shape of space-time. Not a tug, not a push, not an invisible hand reaching across the void, but the natural flow of things moving along curved geometry. Imagine space-time as a soft, responsive fabric. The heavier an object is, the more deeply it presses into that fabric, the more dramatically it curves the world around it. A planet creates a shallow valley. A star makes a deeper well. A galaxy, with its billions of suns, pulls the fabric into a grand spiraling basin. And so, instead of asking why Earth pulls the moon, we ask why the moon follows the contours carved by Earth's presence. It is like a marble rolling along a warped surface. There is no force pulling it inward. The path itself bends. And the remarkable thing is that light, which we so often imagine as invincible, is also compelled to follow those curves. Light travels the straightest possible route, but when space-time itself bends, straight is no longer the line we imagine. It becomes an arc, a sway, a slow drift around mass. This is why starlight curves around galaxies and why black holes wrap light into loops that circle them endlessly. In a sense, matter writes the geometry, and light reads it. Perhaps one of the most humbling consequences of this geometry is the behavior of time. Time, you see, is not universal. It does not beat evenly through the cosmos like a perfect, silent metronome. Instead, it ebbs and flows with the curvature of space-time. Where gravity is strong, time slows. Where gravity is weaker, time runs faster. And although the effect is small on Earth, it is real enough to measure. Your feet age more slowly than your head, simply because they live closer to Earth's center of mass, where curvature is slightly stronger. The difference is microscopic but persistent, a reminder that time itself is part of the cosmic landscape. You may not feel it, but satellites orbiting far above Earth experience time differently. Their clocks tick a little faster because they are in a region where space-time is less curved. Without corrections, the entire global positioning system would drift, and the maps guiding your journeys would unravel. Each time you check a location on your phone, you are using Einstein's equations. You are navigating not through space, but through the warping of space-time. And it is strangely poetic, isn't it, that in 2025, our modern lives depend on a theory once dismissed as pure abstraction. But Einstein's insight did something even more radical. It reshaped our idea of motion itself. In everyday life, it feels natural to think of rest as absolute. You're sitting still, your room is steady, and the world outside seems fixed in place. But in the deeper truth of relativity, there is no universal frame of rest. There is no ultimate viewpoint from which all motion can be measured. Every motion is relative to something else. You are moving with Earth around the Sun, with the Sun around the Milky Way, with the Milky Way drifting through the cosmos, all at once. The absence of an absolute frame means the universe has no single stage. Everything is local. Everything depends on where you are and how you move. What you call stillness is merely a temporary agreement between you and your surroundings. And this relativity extends to time as well. Two observers moving differently or living in different gravitational environments will not agree on the duration between events. Their timelines diverge, not because one is wrong, but because space-time does not offer a single shared rhythm. And that leads us to one of the more subtle and beautiful features of the universe. Space is not perfectly flat. Even where gravity seems weak, space-time carries gentle ripples, slight curves, faint distortions carved across billions of years by the dance of galaxies and dark matter. When we look at cosmic maps, at the distribution of galaxies stretched across the sky, we see the fingerprints of gravity sculpting the shape of the universe. Light traveling from distant clusters is bent and stretched, sometimes magnified, sometimes distorted, all because space-time is not a smooth canvas, but a textured one. You see, when astronomers observe the universe, they are not simply taking pictures. They are reading the imprint of gravitational curvature etched into light's long journey. A cluster of galaxies may appear elongated or multiplied, not because the galaxies themselves are strange, but because space-time between them and us has been shaped by mass. The cosmos acts like a lens, bending light and painting illusions across the sky. This phenomenon, gravitational lensing, is one of the clearest demonstrations that space-time is not flat at all. It is dynamic, structured, and responsive. And, I suppose the more you think about it, the more you realize how deeply this idea changes our place in the universe. We are not separate from space-time. We are expressions of it. Our lives unfold along its curves, our memories formed by its flow, our futures shaped by the trajectories we take within its geometry. And even though relativity is grounded in mathematics, its deeper message is profoundly human. There is no single way to stand in the universe, no single truth about motion, time, or perspective. Everything depends on where you are and how you move. This relativity of perspective becomes especially clear when we try to define simultaneity. We take it for granted that two events can happen at the same time, but in the deeper truth of space-time, simultaneity is not universal. Two observers moving differently will disagree about whether two distant events occurred together or apart. There is no cosmic clock uniting all observers. Time is stitched into space, and the stitching depends on your motion. It is as though the universe whispers to us that perfect agreement is impossible, not because we are flawed, but because the cosmos itself does not provide such certainty. This absence of absolute reference frames also means that the very shape of the universe depends on how we observe it. When we map the cosmos, we must correct for gravitational distortions, for the flow of time at different depths of space-time, for the stretching of light across expanding distances. The maps are not simple drawings. They are interpretations of signals that have been shaped, delayed, bent, and sculpted by relativity itself. In a sense, we are not mapping the universe. We are mapping its curvature. And so, as we let these ideas settle, a picture begins to form in our minds. A universe where mass shapes geometry, geometry guides motion, time flows differently depending on where you stand, and no observer holds the privileged viewpoint. It is a universe of gentle paradoxes, where falling is floating, where stillness is motion, where time is elastic, and where space is anything but empty. Yet, with all this elegance, there is a question that lingers quietly beneath the surface. If mass curves space-time and time itself bends in the presence of gravity, what happens near extreme objects where gravity becomes overwhelming? What happens to time, to space, to the very fabric of reality as we approach the edge of something so dense that not even light can escape? Well, you see, as we follow the story of relativity to its deepest consequences, Einstein's equations guide us toward places where space-time is pushed to its limits, where its curves steepen into cliffs and its smooth flow becomes distorted almost beyond recognition. And that, naturally, leads us into the next part of our journey, where we begin to explore how time behaves when stretched, slowed, or nearly halted, and how our most familiar intuitions begin to unravel under the weight of cosmic extremes. And so, you see, as we follow the thread of relativity deeper into the weave of reality, something even more unsettling begins to emerge. Because once we've accepted that gravity bends the paths of planets and light, we must also accept that it bends something far closer and more intimate, our experience of time itself. And, that's where things become beautifully strange. Time, the quiet companion we assume moves at one steady pace, begins to reveal its true nature and perhaps its true fragility. You know, most of us grow up with the idea that time is universal. We imagine that every clock in the world, whether ticking on a mountaintop or in the depths of an oceanic trench, marches forward at the same rhythm. We imagine that the beating of our hearts, the fading of memory, the growth of a child, all follow a single cosmic tempo. But well, once you look closely, you begin to see cracks in that assumption. Time is not a river flowing at one speed, but a landscape shaped by motion, energy, and gravity. And just as valleys and hills guide the flow of water, the shape of space-time guides the flow of time. Perhaps the first surprising truth is that time can run slow or fast, depending on where you stand in the cosmos. If you find yourself in a region of strong gravity, time dilates, stretching out, slowing down compared to regions of weaker gravity. Near a massive planet, a neutron star, or especially near a black hole, the ticking of time falters. The effect may feel tiny here on Earth, but it is real. If you lived your entire life near the surface of a massive world and someone else lived far above in a weaker gravitational field, the two of you would age at different rates. When you meet again, your timelines would not align. And, this is not imagination. We measure it. Atomic clocks placed at different altitudes fall out of sync. Even a height difference of a few dozen centimeters is enough for one clock to age faster than another. Time is sensitive, almost delicate, shaped by the space it inhabits. But gravity is only half the story. Motion also bends time. If you move very fast, really fast, at speeds closer to light, your time slows compared to someone at rest. And that's the thing. You don't feel it. You could be soaring through space in a smooth, silent vessel, and inside, everything feels normal. Your heartbeat is steady. Your thoughts drift naturally. Your body ages at its usual pace. But to someone watching from a different frame of reference, you are living slower, drifting along a stretched version of time. As one accelerates toward light speed, moments lengthen. A second becomes 2, then 10. Journeys that seem short to you stretch into centuries for those outside. This is not science fiction. It is the geometry of space-time asserting its rules. And if you were to travel far enough and fast enough, you could leap into the future simply by moving quickly through the present. I suppose one of the most haunting examples comes from near a black hole. As you approach its immense gravitational pull, time slows dramatically. To an outside observer, you appear to drift toward the event horizon at an ever-decreasing pace, your movements stretching into near stillness. Light from your body shifts, reddens, fades. Meanwhile, inside your own experience, moments continue smoothly. You do not feel slowed. You simply continue forward while the universe outside races ahead, stars aging, galaxies drifting, perhaps even new civilizations rising and falling while you take just a few steps closer to the horizon. And this leads to a quietly profound truth. There is no shared now in the cosmos. What you call the present is local, personal, woven from your motion, your gravity, your trajectory through space-time. Two people, drifting apart across the universe, may disagree on what events are simultaneous. One might insist that a distant star has already exploded, while the other swears it has not. Both are correct. Simultaneity is not absolute. It is a perspective shaped by the path you take. This idea deepens when we think about moments themselves. You and someone else might watch two events occur somewhere far away. A distant flash of light, a passing comet, a pair of stars colliding. Yet, depending on your motion relative to these events, you might not agree on which happened first. Time does not offer a universal ordering. It offers sequences tied to observers, each stitching together reality as best they can from their vantage points. And perhaps in a quiet way, this makes time feel less like a physical dimension and more like a negotiation between observers and the universe. But well, the strange truth remains. Time is the fourth dimension of space-time, just as real as length or height or depth. When you move through space, you adjust the way you move through time. When you stand still in space, you move through time at your maximum possible rate. The universe keeps the total motion constant, shifting it between space and time like water being poured from one cup into another. You might wonder whether time can stretch the way space stretches. And yes, it can. Time can elongate, compress, distort. In extreme environments, time can nearly halt. Close to a black hole, as gravity bends space-time to the brink of collapse, time flattens, its flow nearly pausing from an outside perspective. And although time never stops completely for any physical object that crosses a horizon, from afar it appears frozen, as though the present has become pinned to space-time itself. This idea makes us wonder about time in its purest form. Does it exist in the absence of change? If the universe were stripped of matter, energy, and motion, would time still tick? We do not know. The question lingers in the borderlands of physics and philosophy. Some theories suggest time might not exist without interactions, while others propose that time is a fundamental property, even in the pure void. But in truth, no measurement has ever captured time in absolute emptiness. It remains a mystery, dangling at the edge of understanding. And, time may also not be entirely linear. We experience it as a sequence of moments, past, present, future, stacked neatly like pages in a book. But space-time may not enforce such ordering universally. There are paths through space-time where cause and effect behave strangely, where loops of time are mathematically possible. No one knows whether the universe permits such structures physically, but the equations seem open to the idea. Time, in that view, does not march in one direction. It can fold, twist, and in rare circumstances, perhaps circle back on itself. But for now, these possibilities remain speculative, waiting for clues from deeper theories. Yet time dilation, the slowing and stretching of time, is not speculative at all. We measure it constantly. Pilots flying high-speed aircraft return with clocks that are out of sync by measurable amounts. Astronauts aboard the International Space Station age ever so slightly slower than those on Earth. The difference is tiny, but it accumulates. Over decades, the offset grows, a reminder that their bodies drift through time differently simply because they move differently or orbit at a different height. When we think about this carefully, something fragile stirs in us. If time is not constant, then our memories, our lives, even our perception of aging are all local phenomena, shaped by the landscape we traverse. Someone in a deep gravitational well ages differently than someone in interstellar space. A traveler Near light speed ages differently than someone at rest. And in a universe with trillions of stars and countless paths, no two beings experience time in exactly the same way. You see, once we accept that, the universe becomes far more intricate. We stop seeing time as a master that rules all equally and start seeing it as a thread woven uniquely into each person's journey. And there's something almost poetic about that. Each life, each moment, each memory is carved into the fabric of space-time, molded by motion, gravity, and circumstance. But as we drift through these ideas, a gentle unease begins to form. If time bends so easily, if it slows, stretches, shifts, and fractures across space-time, then what lies in the regions where gravity becomes violent? What happens to time at the edge of a black hole, where curvature spirals into extremes? What happens in the early universe when space-time itself was new, tight, compressed, and blazing with unimaginable energy? And what happens where space-time tears, ripples, echoes with gravitational waves? Well, you see, as we stand at this threshold, it becomes natural to turn our attention to the one idea that has reshaped cosmology over the past century: the discovery that space is not empty at all, that the vacuum itself is alive with fields, energy, fluctuations, and mysteries, and that this hidden activity beneath the surface of the cosmos might hold the key to understanding not only time, but the very origin of the universe. So let us step carefully from the strange flow of time into an even deeper question. If space is not empty, then what exactly fills it? And how does that hidden structure shape everything we see? You see, as we step gently from the question of time's strange elasticity into the deeper structure beneath it, something even more astonishing begins to shimmer into view. Because if time can stretch and bend, then space, the quiet backdrop we imagine as emptiness, cannot be what it seems either. And, that's the thing I find endlessly fascinating. We speak of empty space as though it were a blank sheet of paper, a smooth silence between stars. But once you lean closer, once you peer into the microscopic depths with both imagination and physics as your guide, you begin to see that space is anything but empty. It is alive, it is restless, it is seething with hidden structure. Perhaps the most surprising truth is that space contains a kind of background energy, a faint but persistent hum woven into its very fabric. Even in regions where matter has vanished, where no particles drift and no light passes, space-time still carries an energy floor. It is like the quiet vibration of a musical instrument waiting to be played. You might call it the bass line of the universe, the low, steady note upon which all other cosmic melodies depend. And, when we look even deeper, much deeper, into the quantum realm, we discover that this so-called emptiness is wildly active. Particles appear and vanish in fleeting moments, flickering like sparks in a dark ocean. Physicists call them virtual particles, but the name is misleading. They are not imaginary. Their effects are real, measurable, woven into the forces that hold matter together. They blink into existence, borrow energy from the fabric of space, then fade before they can be fully observed. It is like watching reality breathe. Well, you see, this constant activity reveals a profound truth. The vacuum is not the absence of things. It is a field, a landscape of potential, where fluctuations ripple and subside. Even if you removed every star, every planet, every atom, this underlying structure would remain. Space does not collapse into nothingness. It has shape, texture, depth, qualities we cannot see with our eyes, but can measure with equations and experiments. This insight becomes even more intriguing when we turn to the quantum scale. Space is not smooth. It is granular, foamy, uncertain. If you could shrink yourself down, far below the size of atoms, below the size of protons, even below the realm of quarks, you might find that space resembles a turbulent sea, churning with fluctuations at unimaginably small scales. These are the quantum foundations of reality, the scaffolding upon which space-time is built. And, These quantum properties influence far more than we might expect. They affect the behavior of light itself. The speed of light, that sacred universal constant, depends on the structure of the vacuum. That structure, with its restless fluctuations, subtly shapes how photons move. Imagine driving across a road. The smoother the path, the faster you can travel. But if the road is textured, even slightly, your movement changes. Light experiences the vacuum in a similar way, gliding across a surface that is not perfectly still. Yet perhaps the most dramatic consequence of the vacuum's hidden structure is the existence of dark energy. You know, there is something haunting about the idea that most of the universe is driven by a form of energy we do not understand and cannot touch. Observations show that space-time is stretching faster and faster. Galaxies are drifting apart not because they are moving through space, but because the space between them is growing. It is as though the vacuum itself is pushing outward, inflating the universe like a quiet, steady breath. This expansion is not uniform. Over billions of years, it has changed the destiny of galaxies. Some will never meet. Some are receding so quickly that light from them will never reach us. And yet, all of this is guided by the energy hidden in the vacuum, in the very fabric of space. And there is something almost poetic about the idea that space can preserve traces of its own past. When ancient events ripple through space-time, collisions of stars, the birth of black holes, those disturbances leave subtle imprints. Space can hold memory, in a sense. It remembers the paths of particles, the curves carved by orbiting planets, the echoes of violent events that happened long before Earth was formed. This cosmic memory is faint, embedded in the curvature, the expansion, the gravitational pattern of the universe. I suppose one of the more intimate truths is that space responds to matter. If you place a mass in a region of space-time, the geometry bends. Remove it, and space-time relaxes. Add motion, and the fabric twists. Add energy, and the fabric stretches. Space reacts the way a living surface might react to weight, pressure, or flow. And in a strange way, we are always reshaping it simply by existing, moving, and thinking. This responsiveness allows space to change its form. In regions of intense gravitational fields, space can stretch like taffy. Around rotating objects, space-time twists, creating a kind of cosmic swirl. In the vast voids between galaxy clusters, space expands like a slowly inflating balloon. And in the quantum realm, it vibrates, flickers, and pulses with fluctuations. You see, once we begin to accept that space is not empty, that it has structure and behavior, something shifts in the way we see ourselves. We start to understand that the universe is not a static vessel containing objects. It is an active participant in every cosmic process. It is the stage, the medium, and sometimes even the storyteller. Even the fabric of the vacuum hints at mysteries we have barely begun to explore. Some theories suggest that the vacuum hides extra dimensions folded tightly into tiny shapes. Others propose that the energy of the vacuum shaped the earliest moments of the universe, controlling how matter formed, how galaxies emerged, how space-time stretched from a point smaller than an atom into the vast cosmic web we see today. And, there's a quiet comfort in knowing that even the emptiest corners of the universe are full of motion. If you were to drift alone between galaxies, surrounded by darkness and silence, you would still be immersed in a sea of fluctuations. Particles would whisper into existence around you. Vacuum energy would pulse softly. Space would stretch beneath your feet, carrying galaxies farther apart at every moment. The universe is never still. But with each new insight into this lively vacuum, a strange question arises. If space is so full of motion, so full of energy and fluctuations, then what sets the ultimate limit on motion itself? What prevents objects from moving faster and faster without bound? What defines the frontier between the possible and the impossible? Well, you see, that question leads us naturally toward the next chapter of our journey. Because intertwined with the restless vacuum is a single constant that shapes the entire structure of reality: the speed of light. It is not just a limit, it is a boundary woven into the very design of space-time. And understanding why light moves as it does, why nothing can outrun it, why it defines what is visible and what is forever hidden, will carry us deeper into the heart of the universe. So let us drift now, gently, from the quantum restlessness of empty space toward the luminous thread that binds space-time together, guiding the flow of information, shaping the horizons of the observable cosmos, and whispering the rules by which reality unfolds. You see, as we drift from the restless energy of the vacuum toward something brighter, something that threads the entire universe together, we inevitably arrive at light itself. And, well, the more you think about it, the more you realize that light is not merely illumination. It is the messenger of the cosmos. It is the ruler against which space-time measures itself. It is the ultimate speed limit written into the architecture of reality. And in a quiet, almost poetic way, light is the reason we know anything at all about the universe beyond Earth. Perhaps the most humbling truth is that the speed of light is not simply fast, it is absolute. Nothing, not matter, not information, not even gravity itself, can outrun it. Einstein didn't choose this number. He discovered it hiding in the equations, like a constant heartbeat beneath everything. And you know, the speed of light is not just a speed. It is a boundary, a horizon, a limit woven into space-time the way a riverbank shapes the course of water. You cannot go faster than light, because space-time will not allow it. It is as if the universe itself whispers, gently but firmly, here and no further. And, this limit does more than restrict motion. It defines the structure of causality. It decides which events can influence each other and which ones remain forever separate. Light sets the rhythm by which the cosmos communicates. Without that limit, you could hear from the future, speak to the past, collapse the order of events, and unravel cause and effect. But because light moves as it does, the universe preserves a cosmic logic, a gentle coherence that holds reality together. When we look at light's journey, we begin to see the shape of the past and the future. Light determines what you can see, what you cannot, what remains forever hidden. The farthest galaxies we observe are not distant in the ordinary sense. They are distant in time. Their light left billions of years ago and only now arrives at our eyes. You are not looking across space. You are looking backward through the river of time itself. Every star you have ever seen is a memory, a delayed whisper, an echo of what once was. And perhaps the most striking realization is that every time you lift your gaze to the night sky, you are performing a kind of time travel. Not the dramatic kind from stories, but a gentle observational one. You are witnessing ancient history written in photons. Some of the galaxies you see may no longer exist in the form they appear. Some stars may have died long ago. Their light simply hasn't caught up to their fate. This means that distance in the universe is not really distance. It is time. A galaxy 1,000,000 light years away is 1,000,000 years in the past. A star 10,000 light years away is 10,000 years in the past. And because the speed of light is finite, the universe becomes a layered history book, each page separated by billions of kilometers and billions of years. When we look outward, we look backward. And this limitation, the fact that light takes time to travel, shapes our understanding of the universe's structure. It defines the observable horizon, the boundary beyond which light has not yet reached us since the moment space-time began. And here we find something astonishing. The universe we can see is not the universe as it is, but the universe as it was. We do not observe the present. We observe the preserved light of the past. The present moment, its galaxies, its structures, its destinies, remains hidden from us. You see, light not only determines what we observe, it shapes what we consider real. It also defines the limit of communication. If you were on a planet orbiting a distant star, and someone on Earth tried to speak to you, their message would take years to arrive. Even if we possessed unimaginable technology, the speed of light sets a hard boundary on how quickly information can travel. These limitations are not technological. They are woven into space-time itself. No matter how advanced we become, we will never coordinate events between distant stars faster than this cosmic pace. The universe imposes patience upon us, and I suppose this makes us reflect on our own perceptions. Our eyes, remarkable as they are primitive time machines. They gather light, interpret it, and let us experience distant events. But that is simply one narrow band of the electromagnetic spectrum. Much of reality remains invisible to us unless we build instruments capable of catching other kinds of light, radio waves, X-rays, gamma rays. In a way, each new instrument allows us to unlock a new slice of the past. This also means that every observation is inherently limited. We see the universe through a narrow window, filtered by light's speed, by the age of the cosmos, by the expansion of space-time itself. And that expansion stretches the light traveling toward us. Photons emitted billions of years ago arrive now elongated, weakened, shifted toward the red end of the spectrum. This redshift is not simply motion. It is a sign that space-time has grown while light traveled through it. And, that idea leads us to something even more subtle. Because if light defines the boundary of the observable universe, then the expansion of space-time defines how that boundary changes. Galaxies far enough away are receding faster than light. Not because they're breaking the cosmic speed limit, but because space-time between us and them is expanding at that rate. Their light will never reach us. They are already beyond our horizon. It is a strange, almost melancholy reality. Entire galaxies, filled with countless stars, countless worlds, countless wonders, are already lost to us, not through destruction, but through distance expanding faster than light can bridge. They drift, silently and forever, beyond visibility. This creates a kind of cosmic solitude. Even in a universe with trillions of galaxies, our observable patch is finite, small, fragile. And the boundary is shrinking over time as acceleration carries more and more galaxies beyond reach. The night sky becomes a museum, preserving ancient light while the real universe moves out of sight. This limitation, though, is also what binds relativity together. The speed of light is not just a number. It is the structure upon which space-time is built. Without it, relativity would collapse, geometry would unravel, cause and effect would lose meaning. Gravity itself, which propagates at light speed, would cease to function in any stable way. And so the speed of light is the backbone of the universe. Perhaps the most astonishing consequence is that your perception of past and future depends on light's limits. Imagine two events occurring far apart. Whether they appear simultaneous or sequential depends on the observer's motion. Light is the ruler by which timelines are stitched together. Without that limit, time itself would lose coherence. You see, light does not simply reveal the universe. It shapes the universe. Its speed defines the structure of causality. Its behavior determines what can be known. Its finite nature creates horizons. Its constancy creates relativity. It is the thread running through every physical law we know. And yet, despite its centrality, light is not the only thing shaped by space-time's geometry. As we venture deeper into regions of extreme curvature, where gravity becomes ferocious and space-time twists into near impossibility, we discover that there are places where even light surrenders, places where its path bends so drastically that it spirals inward, places where the speed of light, that cosmic limit, becomes the boundary between escape and eternal capture. Black holes. They are the natural next step in our journey, the ultimate consequence of curved space-time, the place where light itself bends, folds, and finally yields. And, their existence tells us something profound. Space-time can be stretched to its breaking point. It can collapse, tear, and reform in ways that defy ordinary intuition. So let us move now, gently but inevitably, toward those regions of impossible gravity, toward the places where light cannot escape, where time distorts beyond recognition, and where space-time reveals its most extreme, most mysterious, and perhaps most awe-inspiring face. You see, the moment we allow ourselves to drift from the quiet constraints of light into the darker, more mysterious regions of the universe, there's a kind of hush that settles over the imagination, as though space-time itself is holding its breath. Because now we are approaching the places where its geometry becomes so intense, so violently curved, that even light, that swift, defiant traveler, surrenders. And, this is where the universe reveals one of its most astonishing creations, the black hole. Perhaps it helps to begin slowly, letting the idea take shape in your mind. Imagine space-time as that soft, pliable fabric we've spoken about. Most stars, planets, even galaxies, press into it gently, creating dips and curves that guide the motion of everything nearby. But a black hole isn't a dip. It's a well so steep, so deep, so sharply contoured, that the fabric stops making intuitive sense. The geometry folds inward, directions lose meaning, and everything that wanders too close finds itself drawn toward a center it can never return from. And that's the strange thing. A black hole doesn't pull the way a magnet pulls iron. Objects fall inward because space-time points inward. Every path, every possible direction tilts toward the center. There is no choice in the matter. When physicists say that all roads lead to Rome, they're speaking metaphorically. But inside the domain of a black hole, all possible roads, all geodesics of space-time, really do lead to the singularity. But before we plunge inward, let's pause at the outskirts of one, because even here, far from the crushing core, the curvature of space-time becomes extreme. Light, which normally draws straight lines through the cosmos, begins to bend. It arcs, loops, whirls around the black hole like a moth circling a flame. Some photons skim just close enough to be caught in a precarious orbit, trapped in a perfect ring of perpetual flight. Others spiral inward and vanish. You see, this boundary where light is forced to choose escape or captivity is called the event horizon, and it is one of the most haunting ideas in physics. Not because it is destructive, though it is, but because it marks the line where information itself disappears. Anything crossing that horizon becomes unknowable to the outside world. Time, space, direction, meaning, all begin to unravel. And, here's the part that always makes me pause. To someone watching from afar, an object falling toward a black hole slows down. Its movements stretch, distort, freeze. Time nearly stops near the horizon. Light from the object redshifts into deeper and deeper hues until it fades entirely. It's as though the universe refuses to let anything complete its fall. But from the perspective of the falling object, nothing unusual happens. It drifts past the horizon in a silent crossing, unaware of the transformation the universe assigns to its motion. Inside the horizon, time and space switch roles in a way that feels impossible, yet is dictated by the equations of relativity. Outside, time pushes you forward uniformly. Inside, the singularity becomes your future. Inescapable, inevitable, as unavoidable as next Tuesday. Spatial. Directions collapse into time. You cannot choose where to go. You can only choose how long it takes to get there. Every path leads inward, not through force, but through geometry. And that singularity, well, we speak of it as a point of infinite density, infinite curvature, infinite everything. But we don't truly know what it is. General relativity predicts it, but quantum physics whispers that something else must lie at the core. The theory breaks down there, unable to describe the fabric it itself created. Still, the effects of the black hole extend far beyond this hidden center. They sculpt the orbits of stars. They guide the motion of entire galaxies. In the heart of the Milky Way lies a supermassive black hole around which billions of suns revolve. Without it, the spiral structure of our galaxy might not hold together. In that sense, the black hole is not merely a devourer, it is an anchor. But, black holes are not silent. When two of them collide, space-time rings like a bell. Ripples travel outward, gravitational waves, carrying the energy of that collision across the cosmos. We have measured these waves, these faint tremors passing through Earth as space-time stretches and compresses by amounts smaller than the width of a proton. These waves confirm the deepest predictions of Einstein, that space-time is flexible, that it can wobble, that it can carry sound-like information across billions of light years. Consider that for a moment. A collision of black holes billions of years ago sends a ripple that eventually reaches Earth and jiggles everything we know. Entire planets shift. Not enough for us to feel, but enough for our instruments to detect. It's like hearing the faintest echo of a drum struck in the deep past, yet the drum is two black holes spiraling into oblivion. And the way stars move offers additional proof of these invisible giants. When astronomers observe stars near the center of galaxies, they see them whipping around at impossible speeds, taking tight, intricate orbits around something dark, something massive, something that cannot be seen. Black holes shape these stellar motions, sculpting the dynamics of galactic cores. Perhaps the most mind-bending aspect of black holes, at least for me, is how they stretch space-time itself like strands of cosmic taffy. Near the horizon, objects are elongated by gravitational tidal forces. In fiction, it's called spaghettification, a slightly humorous term for a very real effect. But the science behind it is profound. The difference in gravitational pull between your head and your feet becomes so extreme that space-time distorts your body, not by pulling, but by stretching the paths available to you. Yet even this stretching reveals a deeper truth. Space-time is not rigid. It responds, yields, contorts. It is more like a fluid than a solid. Black holes expose this in the most dramatic way, pushing the geometry to its absolute limits. And, in an even stranger twist, some solutions to Einstein's equations suggest that the interior of a black hole could connect to another region of space-time, perhaps another place, another universe, or another point in time. These hypothetical bridges are known as wormholes. Whether nature permits them to exist is still unknown. They may be mathematical artifacts, or they may hint at something deeper. But the idea that a black hole might serve as a doorway rather than a dead end stirs something ancient in the imagination, the notion of elsewhere. Still, even without exotic pathways, black holes communicate with the cosmos in subtle ways. They power jets that shoot matter outward at near light speed. They shape the evolution of galaxies. Even their deaths, if they die at all, might release radiation as predicted by Hawking, slowly evaporating over unimaginable timescales. A black hole could outlive stars, galaxies, perhaps even the universe itself. But, their true lesson is simpler, quieter, more profound. Black holes show us that space-time is not a passive arena. It is dynamic, responsive, capable of catastrophe and elegance at the same time. They teach us that the cosmos is not built from objects sitting in space. It is built from space itself, twisted, stretched, collapsed, reborn. And once you've absorbed that, once you've felt the sheer strangeness of a place where time nearly stops and space falls inward, a new question begins to approach from the distance. A trembling in the fabric, a whisper riding on the edges of reality. If black holes can bend space-time so violently, if collisions between them can send tremors rippling across the universe, then perhaps space-time itself can ring. Perhaps the universe is not silent at all, but filled with subtle vibrations carrying stories written in the curvature of reality. And you see, that brings us naturally and beautifully to the next chapter, to the discovery that space-time can vibrate, that these vibrations can travel through the cosmos, and that we, tiny beings living on a small blue world, have learned to listen to them. So let us follow those ripples now and learn how the universe sings. You see, once we've stood at the edge of a black hole and felt space-time tremble under the weight of impossible gravity, the next realization rises almost naturally, like a breath the universe has been holding for billions of years. Because if gravity can be bent, twisted, and pushed to its extreme near those cosmic abysses, then surely space-time itself must sometimes shake. And, well, that is exactly what it does. Space-time can vibrate, it can ripple, it can send waves through the cosmos, just as a stone sends waves across a still lake. These are gravitational waves, and they are among the most delicate, most profound messengers the universe has ever allowed us to hear. Perhaps the most poetic way to imagine them is to picture space-time as a vast, taut sheet stretching in every direction. When something immense happens, a collision of black holes, the spiraling death dance of neutron stars, the catastrophic collapse of a massive core, that sheet quivers. The disturbances radiate outward, carrying information not through matter or air, but through the geometry of reality itself. And unlike light, which can be blocked, scattered, absorbed, or bent, gravitational waves pass through everything, through planets, through stars, through gas and dust, through the atoms in your body. They are whispers in the structure of existence, and until recently, humanity had no instruments sensitive enough to hear them. You know, the idea that we could one day listen to the universe seemed almost fanciful for decades. Gravitational waves were predicted by Einstein in 1916, but even he worried they might be too faint, too gentle, too fragile to ever be detected. And yet, they were real. The mathematics insisted on it. Space-time is not rigid, it is elastic. It can carry oscillations the same way a drum carries sound. We simply lacked the ears. Well, you see, everything changed when two detectors, long, silent tunnels of laser beams in Louisiana and Washington, finally heard a faint tremor in the autumn of 2015. The signal lasted barely a fraction of a second, a rising chirp that translated into a soft, ghostly tone. But behind that whisper was a drama of unimaginable scale. Two black holes, dozens of times the mass of the sun, spiraling together, colliding, merging into one. The impact released more energy than all the stars in the observable universe combined. For a moment, and that energy rippled outward as gravitational waves, racing across a billion years of cosmic distance before brushing gently through Earth. Perhaps the most startling thing about these waves is how far they travel. They can cross galaxies, clusters, voids, superclusters, and still arrive mostly unchanged. Like messages smuggled across cosmic deserts, they carry with them the shape of the event that created them, its mass, its rhythm, its violence, its symmetry. When scientists translate these waves into sound, we can actually hear them. Little quivering chirps, rising pitches, soft booms, the universe humming in a register just low enough for human technology to perceive. And, these ripples aren't just beautiful. They are a new way of seeing. For all of human history, astronomy depended on light, visible, infrared, ultraviolet, radio, gamma. But light is easily blocked. Gravity is not. Gravitational waves let us explore regions where light cannot escape. The interiors of supernova cores, the final orbits of black hole binaries, the quiet vibrational patterns of neutron star collisions. These are events we could never observe directly with telescopes, but suddenly, through the tremors in space-time, they become accessible. The universe becomes not only something we see, but something we hear. You know, one of the most astonishing truths about gravitational waves is that they can pass straight through galaxies as though nothing is there. Even dark matter, that mysterious scaffolding of the universe, cannot slow them. This makes gravitational waves pristine messengers, pure signals carrying pure information. They give us access to physics in the most extreme environments, where densities are higher than atomic nuclei and magnetic fields whip matter into exotic forms. In a strange way, every gravitational wave detection is like receiving a letter from a place beyond imagining, a place we could never visit, never see, never touch. Yet its story reaches us effortlessly across the cosmos, and the variety of sources is astonishing. Two neutron stars colliding produce not only gravitational waves but also bursts of light, creating a cosmic flash known as a kilonova. These collisions forge heavy elements, gold, platinum, uranium, the very materials that make up jewelry, electronics, and the deep inner workings of planets. Every gold ring on Earth is, in a sense, a relic of two dying stars spiraling into one another in a kind of cosmic waltz. And gravitational waves tell us exactly when and where such mergers happen. Sometimes the waves come from more exotic sources. A supernova exploding deep within a galaxy may produce a unique, messy signature. A rapidly spinning neutron star with a slight wobble in its crust may create a long, steady hum. Even the background gravitational wave noise left over from the earliest moments of the universe, a faint rumble from the Big Bang, may exist, waiting for a detector sensitive enough to hear it. And the idea that space-time behaves like the surface of a pond is both comforting and unsettling. Because if the universe can ripple, if it can carry vibrations across billions of years, then space-time is not a silent void. It is a medium, a substance of sorts, not in the traditional physical sense, but in the sense that it has behavior, elasticity, response. It can be disturbed, and it can recover. It can wobble. It can oscillate. It can, in its own subtle way, sing. This new kind of astronomy, gravitational wave astronomy, is still young, barely in its infancy in 2025. But already it has transformed our understanding of the cosmos. Before gravitational waves, black holes were invisible unless they interacted with matter. Now, they can announce themselves simply by colliding. Before gravitational waves, neutron-star mergers were theoretical curiosities. Now we can watch them unfold across the sky. Before gravitational waves, the idea of listening to space-time itself felt like poetry. Now, it is a branch of observational science. You see, these waves don't just confirm Einstein's theory, though they do that spectacularly. They reveal that space-time is flexible, dynamic, and alive. Their very existence proves that space-time is not some rigid, unchanging background. It is a physical entity, capable of motion and shape, capable of carrying information, capable of ringing like a cosmic instrument. Perhaps what moves me most is how gentle these waves are. They arrive quietly, trembling Earth by less than the width of a proton. Yet inside that whisper lies the memory of stars that lived and died long before humans existed, long before Earth had oceans, long before galaxies took their modern shapes. These waves are threads of history, stretched across time, connecting the deep past to the fragile present. And, the more we learn to listen, the more stories the universe will tell. One day, future detectors might reveal the faint rumble of the early universe, the aftershocks of spacetime's birth. Or perhaps they will detect the vibrations of exotic objects we cannot yet imagine. Cosmic strings, primordial black holes, or something stranger still. But every new detection deepens a more philosophical truth. If the universe can vibrate, if it can carry the signatures of ancient events across billions of years, then we are not merely watching the cosmos. We are participating in its unfolding. Our instruments are becoming extensions of space-time itself, resonating with the universe, letting us feel its subtle motions. Yet with every answer, a new question rises, gentle but insistent. If gravitational waves allow us to hear the most violent collisions in the cosmos, then what about the quieter, more mysterious distortions of time and space? What about the travel through time itself? Not in fiction, but in the sense allowed by relativity. What about the paths through space-time that twist so sharply they might allow shortcuts, loops, possibilities beyond our everyday intuition? Well, you see, once you've listened to the universe's vibrations, it becomes almost impossible not to wonder what else space-time might allow. What deeper structures it might hide. Whether time can be navigated the way space can. whether the cosmic fabric contains tunnels or curves that could turn science fiction into something more tangible. And so, from the gentle ringing of space-time, our journey naturally shifts toward one of the boldest ideas in physics: the possibility that time itself is not fixed, that the future can be visited, that the past is a puzzle, and that space-time might contain pathways stranger than any star or galaxy. Let us take that step now, into the realm where time becomes a direction we might one day learn to explore. You see, once we've learned to listen to the universe, not with ears, but with instruments delicate enough to detect the trembling of space-time, a new kind of wonder begins to settle in. Because if space-time can ring, if it can vibrate like a vast cosmic drum, then perhaps it can also twist into shapes strange enough to bend time itself. And, well, that's where our journey now leads, into the realm where time is no longer simply something that flows, but something that can be manipulated by motion, gravity, and the deep geometry of the universe. Perhaps the quiet truth at the heart of this chapter is that time travel, at least to the future, is not science fiction. It is baked into the structure of space-time. You can move through time at different rates simply by changing how you move through space, or where you sit in a gravitational field. In that sense, every astronaut aboard the International Space Station is a time traveler, aging more slowly than you and me, drifting ever so slightly into the future ahead of us. It's subtle, yes, but undeniable. Relativity says so. Experiments confirm it. You see, the faster you travel, the slower your time flows compared to someone at rest. Accelerate to a significant fraction of light speed, and seconds become minutes for those you leave behind. Push harder, approach the speed of light, and the time dilation grows extreme. A journey that feels like 1 year to you might correspond to a decade on Earth. A decade to you might be centuries on Earth. The universe allows this. In fact, the universe insists on it. That's just how space-time works. And, gravity does the same thing. If you linger near a massive object like a neutron star or a black hole, time for you slows, relative to someone far from the gravitational well. You could descend toward a black hole, not too close, of course. Spend what feels like a short afternoon near its enormous mass, and return to find that years have passed elsewhere. In that gentle, surreal way, relativity offers a real mechanism for traveling into the future. But traveling into the past, well, that's where things become slippery, uncertain, and profoundly mysterious. You know, physics doesn't forbid it outright. Not in the deep mathematics of general relativity. There are solutions to Einstein's equations that allow loops in space-time, paths that could, at least in principle, lead you back to an earlier moment. These are called closed time-like curves, timelines that fold back on themselves like a strand of spaghetti bent into a loop. And some space-time geometries naturally create such loops. The interior of certain black hole models, the rotation of hypothetical objects like Kerr black holes, even massive rotating cylinders, if they existed, could twist space-time enough to loop time back upon itself. The idea is deeply unsettling, perhaps even frightening. But, the mathematics is there. It does not recoil from the possibility. One of the most famous concepts in this landscape is the wormhole, a tunnel through space-time connecting two distant points. It's the ultimate shortcut, the dream of every traveler who has ever wondered what lies beyond the next star. But wormholes aren't merely shortcuts in space. They're shortcuts in time. Tilt the geometry just right. Accelerate one mouth of the wormhole relative to the other. Place it near a massive object long enough, and you create a time difference between the two ends. Step through, and you might emerge at an earlier moment. It sounds fantastical, and perhaps it is. We don't know whether wormholes exist. Even if they do, they may collapse before anything can pass through. Or they may require exotic forms of matter to stay open. Matter with negative energy, something we've never seen on a macroscopic scale. But relativity does not forbid them outright. And that, I suppose, is enough to keep the idea alive, suspended between the edge of science and the edge of imagination. Still, even if such paths exist, time travel brings paradoxes. Deep, unsettling paradoxes that force us to confront the very nature of cause and effect. The most famous is the grandfather paradox. If you travel into the past and change something essential, prevent your grandparents from meeting, for instance, do you erase your own existence? Or does the universe adjust itself to prevent such contradictions? Some physicists argue that you simply cannot change events that have already unfolded. The timeline is self-consistent. Whatever you do in the past was already part of the past. If you go back in time, your actions become woven into the history you thought you were rewriting. The paradox dissolves into inevitability. Others suggest the universe might split, branching into separate timelines like the growth of a cosmic tree. In that view, you don't change the past, you create a new one, a new world, a new thread of reality. And, there are theories proposing something even more subtle. That space-time itself has a built-in mechanism, a kind of cosmic autocorrect that prevents paradoxes by subtly adjusting outcomes. Push causality too hard, and space-time nudges things back into alignment, yet no experiment has ever confirmed any of this. We cannot step into the past to test it. We can only follow the equations, speculate, debate, and wonder. And while time travel into the past remains a mystery, future travel is not only possible, it is unavoidable. Time does not flow Odinaka for everyone. Two people taking different paths through space-time can age at different rates, and in a universe filled with gravitational wells, accelerating objects, cosmic voids, and expanding space, time becomes as malleable as clay. This makes you think differently about the future. Not as a straight line ahead of us, but as a landscape shaped by the choices we make. Not moral choices, but physical ones. Where we travel, how fast we move, how deep into gravity wells we descend. Every traveler moves through a different river of time. And perhaps the most intriguing truth is that space-time might contain shortcuts that don't merely bend time, but reshape it. Wormholes, as we've said, might connect distant regions of the universe instantly. They might also connect different moments. A wormhole entrance in orbit around a black hole would experience time more slowly. Step through the calmer entrance and exit the accelerated one, and you emerge into the past relative to the path you took. Yet the existence of such phenomena depends on the nature of space-time itself, on what it allows, on what it prohibits, on whether exotic matter exists, on whether quantum gravity, a theory we have not yet discovered, imposes rules we do not yet understand. You see, the deeper we go, the more time feels like a dimension we've barely begun to comprehend. We move through it, but we do not command it. We measure it, but we do not see it. We imagine it as linear, but it may be folded, twisted, perhaps even granular at the smallest scales. And the possibility of looping paths, shortcuts, and paradoxes hints at mysteries still hidden behind the curtains of our equations. What strikes me, though, is how fragile our intuition is. We imagine time as a river flowing uniformly, but relativity shows us it is more like a landscape of hills and valleys, cliffs and tunnels, smooth plains and sudden drops. Where we stand shapes how time treats us. And, perhaps one day, far in the future, humanity will learn to navigate those hills with intention, rather than simply drifting along them. But even now, long before such mastery is possible, relativity reminds us that time is not the ruler of the universe. Space-time is. Time is simply one direction in that deeper structure, and motion through space-time changes our experience of it. Yet as fascinating as time travel is, as intoxicating as the idea becomes once we realize how fluid time truly is, there is an even deeper question waiting in the wings. Because if space-time allows such paths, if it can bend in such dramatic ways, if it contains the seeds of shortcuts and loops, then what can we say about its origin? Where did space-time come from? What happened before its beginning, if before even makes sense? Well, you see, that leads us into one of the most profound and humbling chapters of all, the moment when space-time itself was born. the moment when the cosmos emerged not into space, but with space, not into time, but with time, the moment of the Big Bang, where everything began, including the fabric we've been traveling through. Let's step toward that beginning now. You see, when we follow the twisting possibilities of time, its loops, its dilations, its strange flexibility, there comes a moment when we must ask the most fundamental question of all. Where did this fabric begin? Because if time can stretch and bend, if space-time can ripple with gravitational waves and twist near black holes, then surely it must have had a moment of birth. And, well, that moment is what we call the Big Bang. Not an explosion in space, but the moment space itself appeared, the moment time itself began its long unfolding journey. Perhaps the most humbling truth is that space-time did not arise within a pre-existing void. There was no emptiness waiting to be filled. There was no before, at least not in any sense our minds can comfortably grasp. The Big Bang is not the story of something expanding into something else. It is the story of expansion itself becoming possible. The story of a fabric that was once compressed into a state so dense, so hot, so unimaginably small that all distinctions, space, time, matter, energy, blurred into one unified, seething essence. You know, we sometimes imagine the early universe as a fiery sphere glowing like a star. But, that picture is misleading. In the beginning, the universe was smaller than an atom, smaller than a proton, smaller than the tiniest structure physics can describe. Everything, galaxies yet unborn, the seeds of stars, the foundations of chemistry, were compressed into a point so tight that language fails us. And within that density, time had no meaning. Asking what happened before the Big Bang is like asking what lies north of the North Pole. The question dissolves in the very act of asking. But the moment expansion began, space-time blossomed into existence. Space stretched, time began to flow, and the universe surged outward at speeds that defy ordinary intuition. This was not matter racing through space. This was space itself expanding, pulling galaxies apart in a cosmic tide that continues even now. And, as the universe expanded, it cooled. In those first fractions of a second, temperatures were so high that particles flickered between existence and non-existence. Quarks drifted free. Gluons danced without structure. Then came the moment of confinement, when quarks locked together into protons and neutrons. A few minutes later, the first atomic nuclei formed in a quiet, fragile ballet choreographed by the expanding space-time. Perhaps what amazes me most is that the early universe was almost perfectly uniform, smooth to one part in 100,000. And yet those tiny imperfections, those minute fluctuations in density, became the seeds of every galaxy we see today. Imagine that. The entire cosmic web traced back to tiny ripples in the fabric of space-time itself. These ripples left behind a record, a relic, a glow that fills the entire sky, invisible to our eyes but detectable with the right instruments. This is the cosmic microwave background, the afterglow of the Big Bang, a snapshot of the universe as it was just 380,000 years after its beginning. It is space-time's baby picture, and in it we see the fingerprints of the early cosmos, its density, its temperature, its geometry. This faint radiation confirms that the universe once existed in a state of extraordinary heat and density. And, perhaps the most delicate detail hidden in that ancient light is that the universe was astonishingly flat, not perfectly flat, but so close that it requires explanation. In a curved universe, space-time could be shaped like a sphere or like a saddle, but observations suggest an astonishing near balance. Why? Some theories propose that the universe underwent a brief period of inflation, a rapid expansion that smoothed space-time, flattening its wrinkles like steam smoothing a cloth. Inflation also explains why the universe seems uniform in all directions, even though distant regions have never communicated at the speed of light. They were once close, perhaps unimaginably close, before inflation stretched them apart faster than light could travel. Not in violation of physics, but because space-time itself can expand at any speed. You see, the early universe was not simply chaotic. It was structured in a way that allowed stars to form, galaxies to take shape, and eventually life to arise on a small blue world billions of years later. If space-time had expanded just a little faster or slower, the cosmos would have torn itself apart or collapsed into itself. But instead, something exquisite happened. The universe balanced delicately on the edge of possibility. As billions of years passed, galaxies formed and drifted, stars were born and died, and space-time continued to stretch. Even now, in the quiet night sky, that expansion is ongoing. Galaxies race away from each other, carried outward by the growth of space. Some accelerate so rapidly that their light will never reach us. In that sense, the universe's expansion is not just a physical fact. It is a horizon, a limit on what we can ever know. And, we often imagine the universe cooling forever, spreading thinly into darkness. But the truth is more complex, because even today, space-time still carries subtle traces of its origin. Tiny anisotropies in the cosmic microwave background, delicate gravitational waves echoing from ancient events, the structure of galaxy clusters shaped by fluctuations older than time itself. The early universe left scars and signatures everywhere. And we, standing on Earth in the year 2025, have learned to read some of those signatures. Not all, not yet, but enough to know that the Big Bang was not a singular explosion, but an emergence, a transition, a birth of something deeper than space, deeper than matter, the birth of the very stage upon which all existence would unfold. And, the closer we look, the more mysterious that birth becomes. What triggered inflation? What shaped the earliest fluctuations? Was the Big Bang truly the beginning, or was it the end of something else? Did space-time emerge from a quantum foam, a previous universe, a higher dimensional structure? We don't know. Not yet. But the idea that the Big Bang marks the absolute beginning of everything may not be the full story. Some models suggest our universe might be one bubble in a vast multiverse, each bubble with its own space-time, its own laws, its own beginning. Other theories propose that universes may collide, imprinting signatures on each other, or that black holes might spawn new universes inside their singularities, each with its own version of space-time. You see, the Big Bang does not close the door on wonder. It opens it. And as we step away from that first moment, that incandescent birth of space-time, the next question rises almost inevitably. If our universe emerged from such beginnings, might there be others? Might space-time exist in forms we cannot yet imagine, branching, colliding, multiplying beyond the reach of our observations? Well, that leads us directly into the next chapter, into the possibility that our universe is not alone, that space-time itself might be only one layer of a structure far grander than anything we have ever conceived. Let's walk into that possibility now. You see, once we've traced space-time back to its first breath, that incandescent moment when space and time themselves unfurled from a single primordial seed, we reach a threshold where the questions grow even larger, even more unsettling. Because if our universe had a beginning, if it carries the scars and whispers of its earliest moments, then perhaps it is not the only one. Perhaps space-time is not singular, but part of something far richer, far stranger. And, well, that is where the multiverse steps quietly into view. It's tempting to think of the universe as everything there is, that the galaxies we see, the cosmic web spreading across billions of light years, represent the full story. But the more deeply we peer into cosmology, the more evidence begins to stir that space-time itself might exist in multiple forms. That what we call the universe may be just one bubble in a vast cosmic ocean. And you know, one of the earliest clues comes from the simple realization that space-time need not be shaped the same way everywhere. In our universe, space-time is mostly smooth and nearly flat, stretching out like an immense sheet. But the laws of physics don't forbid radically different shapes. Space-time could curve inward or outward. It could fold, loop, ripple, or twist in ways our intuition can't easily grasp. And nothing in the equations of general relativity declares that only one such space-time is allowed. So the question naturally arises, if space-time can exist in many forms, why should only one universe exist? Some theories suggest that the Big Bang wasn't unique. That inflation, that brief, furious stretching of space-time in the universe's earliest instant, might produce countless regions of space that become isolated from one another, each forming its own universe with its own version of space-time. These bubble universes could expand indefinitely, like droplets forming on the surface of a boiling pot. And inside each bubble, the laws of physics might differ slightly, or even dramatically. Our universe could be just one bubble among many. And, the idea that each universe has its own space-time is not merely speculative fantasy. It follows directly from the mathematics. If inflation continues eternally in some regions, then new bubbles of space-time constantly butt off from the inflating background. Each bubble cools, expands, and evolves into something like, or unlike, our universe. It's a strange thought, isn't it? That somewhere beyond the edge of what we can observe, another universe might be expanding with its own galaxies, its own stars, its own set of physical laws shaping its destiny, perhaps even its own version of time. You see, if different universes have different space-time structures, then time itself may not tick the same way everywhere. In one universe, time might flow quickly, in another slowly. In one, time could behave linearly. In another, it could cycle or branch. Some universes might allow complex structures like life. Others might remain forever barren. And then, of course, there's the question of what lies between these universes, if between even makes sense. Some theories suggest that the space between universes isn't space at all, but something deeper, a higher dimensional substrate in which universes float like bubbles in foam. If that's true, then space-time is not the deepest layer of reality. It is a surface, a boundary, a localized phenomenon arising from something more fundamental. And if universes are indeed like bubbles, then what happens when bubbles collide? It's a question that cosmologists take seriously. If our universe once collided with another, that collision might have left a signature smeared across the cosmic microwave background. A faint circular pattern, a bruise in space-time. Researchers have looked for such signs. Some claim hints. Most remain skeptical. But the search continues because the implications are extraordinary. A collision between universes would mean that our cosmos once brushed against another, exchanging energy, distorting the early geometry of space-time, leaving behind a faint memory etched in radiation. Imagine that. The ghostly fingerprint of another universe imprinted upon our sky. But the multiverse idea doesn't end there. Some versions of string theory suggest that space-time might have more than 3 spatial dimensions. Our universe could be a 3-dimensional membrane floating in a higher dimensional space. Other universes, other membranes, might float alongside ours. And occasionally, these membranes could collide, triggering cosmos, creating events reminiscent of the Big Bang. In that picture, universes are not bubbles, but sheets. Not droplets, but membranes drifting in a deeper ocean. And collisions between them might spark new beginnings, new bursts of space-time, new realities. It's dizzying, I know. But there is a quiet beauty in imagining space-time not as the limit of everything, but as one layer among many, like a page in a book whose other pages we cannot read, but whose presence we can sometimes infer by the slight pressure they exert. Another version of the multiverse emerges from quantum mechanics. In that view, every quantum event, every choice, every possibility, splits reality into new branches. Each branch becomes its own universe, complete and consistent, with its own space-time. In such a framework, the multiverse is not a distant landscape, but a constantly branching tree growing at every moment. And when you consider that picture, a strange philosophical idea emerges. If every possible history exists in some branch, then our universe is merely one thread in an ever-branching tapestry, woven from the fabric of space-time and probability. Time in that view is not a single line, but a sprawling structure of alternate paths. But even if one hesitates to embrace such ideas fully, it's hard to deny that the multiverse has become a serious hypothesis in modern physics. Not proven, not settled, but taken seriously enough that researchers look for evidence in cosmological maps, in particle physics experiments, in the structure of gravitational waves. And perhaps the most haunting implication is that if multiple universes exist, we might never reach them. The space-time of our universe is self-contained. If another universe lies beyond our cosmic horizon, no signal can cross the gap. No spaceship can travel there. Even wormholes, if they exist, may not bridge universes, but only connect distant regions within a single one. Yet despite the unreachability, the multiverse idea forces us to confront our cosmic modesty. It suggests that our universe is not the whole of reality, but a small, local patch in an incomprehensibly vast structure. It humbles us in the same way that learning Earth was not the center of the solar system, and the solar system not the center of the galaxy, and the galaxy not the center of the cosmos. You see, whenever humanity believes it has reached the edge of understanding, the universe gently reveals that there is more space beyond our maps, more time beyond our lifetimes, more universes beyond our horizons. And, if the multiverse is real, then space-time is not just the stage of our universe. It is a layer in a deeper architecture, a local manifestation of something perhaps more fundamental, more abstract, more mysterious. In that sense, space-time might not be the whole story, but a chapter, one among many written across dimensions we cannot perceive. But here, a new question begins to rise. If space-time in our universe is so finely structured, full of curvature, waves, quantum fluctuations, then what happens to this structure at the smallest scales? What happens when we reach the very bottom of reality, where quantum mechanics and gravity collide? Well, you see, that leads us naturally to the next part of the journey, into the strange, jittery realm where space-time itself may become granular, where distances blur, where time flickers, and where quantum physics reshapes everything we thought we understood. Let's step into that quantum realm now. You see, once we allow ourselves to imagine that our universe might be only one bubble in a vast cosmic ocean, floating alongside countless others, something else begins to stir beneath the surface of our thoughts, a deeper question, quieter, but more fundamental. If space-time can exist in many forms, if it can stretch, ripple, collapse, or even multiply across a multiverse, then what is space-time made of? What lies beneath its smooth appearance? And, well, that question leads us to a frontier far stranger than galaxies or black holes. It leads us into the quantum realm, where certainty dissolves, where reality flickers, and where the very fabric of space-time begins to blur. Perhaps the most humbling truth is that space-time, which seems so continuous, so seamless in our everyday experience, may not be smooth at all. If you were to shrink yourself, not to the size of an atom, not even to the size of its nucleus, but far, far smaller, down to the Planck scale, a trillion times smaller than anything we can observe, the structure of space-time would begin to break apart. It would jitter, foam, fluctuate like the surface of a boiling sea. Distances would cease to be definite. Time would stutter and skip in tiny, unpredictable jumps. Geometry itself would lose meaning. And you, drifting through this quantum surf, would find that the familiar concepts of here and now simply evaporate. You know, we often imagine that the universe has a smallest unit, a kind of indivisible pixel of existence. And, in some ways, that might be true. At the Planck scale, a length so small it defies imagination, space-time may become quantized, divided into tiny chunks, like the grains of sand that make up a beach. This idea is not proven, but many theories suggest it. Loop quantum gravity imagines space-time woven from loops of geometry. Other proposals see space-time as a vast network of discrete nodes, connected by relationships rather than distances. In such a world, space is not continuous. It is composed. And if that is true, then everything we experience, motion, time, light, emerges from an underlying structure more fundamental than the space-time we know. You see, the quantum realm does not allow us the comfort of smoothness. At that scale, uncertainty dominates. Position and momentum cannot both be known precisely. Energy flickers unpredictably. Particles appear and disappear in spontaneous bursts. And this jittery, restless behavior may not be confined to particles alone. It might affect space-time itself. Quantum fluctuations could make space-time shiver, wrinkle, and ripple on incredibly small timescales. Imagine trying to draw a straight line on a surface that vibrates violently and unpredictably. That is what trying to define geometry at the quantum level might be like. The familiar laws of relativity, which treat space-time as smooth, break down completely. And, that breakdown leads us to a profound problem. General relativity and quantum mechanics do not get along. They are the two great pillars of physics, and yet they contradict each other in the environments where they both should apply. Near singularities at the birth of the universe, or in the tiniest creases of space-time. Relativity describes the large-scale structure of the cosmos. Quantum mechanics describes the smallest phenomena. But there is no unified language that speaks both truths at once. Physicists have been searching for such a theory, a quantum theory of gravity, for decades. It remains one of the great unsolved mysteries of modern science. String theory offers one possible answer. It imagines that the fundamental building blocks of reality are not particles, but tiny vibrating strings. Different vibrations correspond to different particles. A photon here, a quark there, a graviton somewhere else. And in this picture, space-time itself is not a background in which strings vibrate. It emerges from the vibrations, like a melody emerging from the strings of a violin. The geometry we observe, the curvature, the motion, even the dimensionality, is simply the collective behavior of these microscopic strings. But for string theory to be consistent, space-time must have more than 4 dimensions. Some versions require 10, others 11. These extra dimensions, curled tightly into spaces smaller than atoms, might influence the physics we observe even though we cannot see them. They may shape the masses of particles, the strength of forces, the very structure of matter. And, they hint that the space-time we experience, with its 3 large spatial dimensions and 1 flowing time, may be only a shadow of a deeper, richer structure. Other theories push even further. Some propose that space-time is not fundamental at all, that it emerges from entanglement, the deep, mysterious connection between quantum particles. In that view, space exists because particles are entangled. Remove the entanglement, and the space dissolves. Time, too, could be emergent, arising from changes in entanglement patterns. The entire universe becomes a kind of information network. Space-time woven from quantum relationships rather than physical distances. It's a strange idea, I know. But the deeper we push into the quantum world, the more it seems that reality may not be built from matter or energy, but from information itself. Space-time becomes not a substance, but a reflection of how information is arranged. And yet, despite these possibilities, we have no experimental evidence at such small scales. The Planck length is far beyond our reach, a scale so tiny that even the most advanced instruments humanity imagines cannot probe it. But we do see hints, faint suggestions that quantum effects ripple through space-time. Black hole thermodynamics, for instance, suggests that space-time has entropy, a measure of the information it contains. And the holographic principle proposes that the entire volume of a region of space can be described by information encoded on its boundary, as though reality itself behaves like a hologram. You see, the quantum realm forces us to rethink everything. Space may not be continuous, time may not be smooth, Space-time might be granular, emergent, or holographic, and quantum fluctuations might constantly blur the geometry we take for granted. In this view, the universe is not a static stage. It is a dynamic, jittery fabric, intertwined with uncertainty at every level. And perhaps that is why general relativity and quantum mechanics resist unification. They describe worlds so different that reconciling them requires rewriting the very foundation of physics. Relativity demands smoothness. Quantum mechanics demands uncertainty. Bringing the two together may require a new language, one we have not yet learned to speak. Yet in the middle of this struggle, string theory whispers a seductive idea. It suggests that the universe at its deepest level is music, vibrations of tiny objects in multidimensional space. Gravity itself emerges from one particular vibration, the graviton. Space-time is not a container but a resonance. And if that is true, then the structure of space-time may be nothing more than the collective harmony of quantum notes. But even string theory faces challenges. It predicts many possible universes, a vast landscape of solutions, each with its own space-time. And perhaps that is where it intersects with the multiverse. If each possible configuration of extra dimensions produces a different universe, then the multiverse may not be speculation at all. It may be a mathematical necessity. The quantum world also forces us to consider that space-time might have hidden dimensions, not vast ones, but curled up so tightly we cannot detect them. These dimensions might shape the fundamental constants, guide particle interactions, or influence gravity in subtle ways. And although we cannot see them, they may be woven into every point of space-time, like threads running through a tapestry. You see, the closer we look, the less certain we become. Reality, at its most fundamental, may not be what it seems. Space may not be smooth. Time may not be absolute. Space-time may not be continuous. And the fabric that holds the universe together might be composed of tiny, fluctuating, vibrating, ephemeral structures. And there is something strangely comforting in that. It means that the universe is not rigid. It is flexible, adaptive, alive with subtle motion at every scale. And the very uncertainty at the heart of quantum mechanics may be the reason space-time can bend, ripple, and stretch the way it does. But as we wander deeper into this quantum labyrinth, a new question begins to form. Soft at first, then insistent. If space-time is built from something deeper, if its geometry arises from quantum processes, then what does that say about the ultimate nature of reality, about consciousness, about existence itself, about the final? Questions that hover at the edge of science and philosophy? Well, you see, that leads us to the last chapter, the place where curiosity becomes reflection, where physics touches mystery, and where space-time might reveal not only how the universe works, but why there is a universe at all. Let us walk into that final realm now.